1 minute recording. Okay. A very warm welcome to day 4 of our AICT sponsored ATAL FDP program organized by Department of Electronics and Communication, Mahakal Group of Institute, Ujjain. Today we have a speaker from the top 5 university in the United Kingdom or England, Dr. Akash Bansal sir from Loughborough University. He is serving as a professor in that university. For formally introduced, I request Dr. Saurabh Gaur sir, Head of Department Electronics and Communication, to formally welcome and introduce Dr. Akash Bansal sir. Over to you, sir.
Thank you, Dr. Pant. Good evening, everyone. May I audible?
Yes, sir.
Yeah, thank you. It's my absolute pleasure and honor to introduce our distinguished speaker, Dr. Akash Bansal, member of IEEE. Dr. Bansal is the Royal Academy of Engineering UK Intelligence Community Research Fellow and Professor in Applied Electromagnetics at Loughborough University, UK. He received his Bachelor of Technology in Electronics and Communication Engineering from Guru Gobind Singh Indraprastha University, Delhi in 2017 and did his PhD dissertation on active millimeter wave beam steering antenna array systems for 5G and beyond from Loughborough University, UK in 2022. Previously, he worked as a research associate with CSIR, that is Central Electronics Engineering and Research Institute, Pilani, from 2017 to 2019, and as a future network engineer for Satellite Application UK from 2022 to 2023. His research interests includes beam farming, beam steering antennas, intelligent metasurfaces, dielectric lenses, antenna arrays, antenna for space, and orbital angular momentum waves. He has received IEEE Richard E. Mervyn Student Scholarship in 2016, CSIR Young Engineer Award in 2018, Loughborough University's Sir Robert Martin University Prize in 2020, Electronics Weekly's Bright Sparks Award in 2020, and Loughborough University's Doctoral Researchers Presidential Award in 2022. Sir, may I now request you to kindly address the participants. Thank you.
Hi, everyone. Thank you so much for the invite, and thank you so much for the kind introduction. Congratulations on organizing such a nice faculty development program. I can see there are more than 100 people attending it, which is really nice. So yeah, today I'll be talking a bit about some of the work that we've been doing on RF front-end systems, talking a bit about 3D printing, optically transparent antennas, metasurfaces, a bit of work we do on reconfigurable intelligent surfaces, etc. And we can go step by step. There are about 5 or 6 different projects I'll be talking through, and I'll be happy to take any questions. If you have any questions in between, just put them in the chat box and I'll read them in between. If not, we can just go through some questions at the end. So let me just share my screen. Please, can you confirm if you can see my screen?
Yes, sir.
Okay, perfect.
PPT is visible, sir.
Awesome. All right. So going ahead. Today we'll be talking about recent advances in RF front-end systems, from 3D printing to optically transparent antennas and transparent structures. And we'll be talking a bit about different works. So as Mohit mentioned, that I am a lecturer and a Royal Academy of Engineering Research Fellow at Loughborough University. Loughborough is based in the middle of the UK, right in the center of England. And we are one of the top universities doing a lot of work on electromagnetics, on telecommunications, sensing, mechanical engineering, photonics, etc. Our group, Wireless Communications Research Group, mostly focuses on communication and sensing side of things from an electromagnetics perspective, and we do mostly RF front-end systems. We have a group of about 5-6 PhD students right now, and about 3-4 four postdoctoral researchers, one professor, uh, two senior lecturers, and one lecturer, which are equivalent to assistant and associate professors. So yeah, to, so to continue with the work, so I'll be talking about 4 or 5 of the projects that we're doing: SciMeta, novel reconfigurable antennas, ANISAT, and Transmeta. And I'll show you some of the results we have got, some of the research that we've been doing. And then from there, we'll slowly transition into the different kind of work and different kind of facilities we've got. So SciMeta was one of our earlier projects, which finished late last year, so around October, November last year, which was led by Loughborough University, and it also had Oxford, Queen Mary's, University of Exeter, and Sheffield as team partners on it, and they were all contributing from different perspectives. SciMeta was completely focused on using 3D printing for RF applications, all sorts of RF applications, developing filters, antennas, metasurfaces, any sort of RF devices, capacitors, inductors, etc. And I'll show you some of the outcomes of this project, some of the interesting work that we've done. So to start with, we all know what 3D printing is. It's a fairly common technology today. I believe almost every university today at least has one 3D printer globally. So I'm guessing every university over here participating has a 3D printer. One of the beauties of 3D printing is it does not limit you to a 2D structure that we've been limited to so far in regular antenna design, where we do mostly PCB structures, where we are limited to 2D structures. Or if you have to do a proper 3D structure like a dish antenna, you have to machine a metallic structure. With 3D printing, you can actually print either a dielectric or a pure metal structure into different shapes and sizes that could not be envisioned before. And by changing the grading, by changing different densities of the material, you can actually start introducing new material properties into it. You can change the permittivity of the material. You can change loss tangent of the material, etc. And again, it's very environmental friendly because there is less waste. Whatever waste that is generated, you can actually reuse it and recycle it to, again, use it for different sort of 3D printing. So there are a lot of materials available in the market. Here is a list of certain materials that we use in our lab. Two of the materials which I believe a lot of you would be familiar with are PLA and ABS. PLA is polylactic acid thermoplastic material, which is most commonly used in any sort of 3D printing activity anywhere. And ABS is another very, very commonly used material, which you would see almost everyone uses in all sorts of 3D printing applications. And interestingly, both of them presents really good dielectric properties. So PLA generally has a relative permittivity of 2.7, which is very, very, very good for any sort of RF applications. And it has a loss tangent of about 0.001, 0.002. ABS, on the other hand, is slightly different. It has a relative permittivity of 2.2, very close to Rogers 5880, 5870. And the loss tangent is also quite low. It is about 0.003, 004, which is again an excellent material. You can see there are a lot of other materials like HIPS, TPU, preperm, etc., which are like ceramic loaded materials, which are again very easily available in the market and you can buy them. That actually has decent loss tangent, very low, around the range of 0.002 to 0.005, and they can generate a permittivity up to 12. We have recently invented more materials. We have actually come up with more materials, and we can go up to permittivity of 30 using 3D printing. I know of another group in Italy that can actually go up to 35 or 40. So you can see how easy it is to do different sort of materials and different sort of relative permittivities by just using simple 3D printing. So going ahead. So how does 3D printing works? One of the key points is 3D printing, if you're doing like an FDM based technique where it is one layer at a time being printed, then you imagine your element is 100% infill density, but in reality, there are always gaps and creaks in between, as you can see in this 3D structure over here. Let me see if I can do a pointer. Okay, I don't know if you can see the pointer on the screen. Let me just quickly. Okay, can anyone confirm if you can see a pointer on the screen?
Yes, sir.
Okay, perfect. So you can see there are small creaks, small gaps in the 3D printing structure, which you can see has a extremely enlarged, zoomed in view of the structure where there are air gaps. So in reality, when you say the material has a permittivity of 2.7, this might actually reduce your overall infill density, and it reduces it down to about 95% or 90%, which will reduce your dielectric permittivity as well. Now, that is in general for simpler antennas, it is not a problem, but these air gaps become a massive problem when you're looking for practical applications like space. If you're 3D printing an antenna for space, you cannot have that gap because that will start creating air pops, which will blast off the whole structure in space. And hence, you have to be very, very careful about how these gaps are forming. And hence, it's very important to do the research about how does 3D printing work and how can we actually utilize it for different sort of structures. So we've done quite a lot of work on. Wait, is the screen stuck here? Sorry, guys. I'll just reshare the screen. Okay, I think the screen should be visible again now. Yep. So now going ahead, you can do quite a lot of different sort of versions by changing the permittivity by changing the infill density of the material. You can change the relative permittivity and loss tangent as well. As you can see over here, your relative permittivity is changing from 1 to about 10 by just changing the infill density. By infill density, I mean how much percentage is the actual material versus how much percentage is the air. If you're using any regular 3D printer, like for example, an Ultimaker that uses a Cura software, it actually allows you to define what sort of 3D printing do you want, how much air gap do you want, and how much material do you want. And during the printing process, it can create those air pockets in between. And you can use that variation in relative permittivity in your design to achieve different performances. And hence, you can achieve completely new application like lensing behavior in a simple 3D structure, which I'll show you later on. So when we do these sort of 3D printing work, we have to actually characterize a lot of material to understand its relative permittivity. So we've got 4 different techniques in our lab through which we actually characterize any sort of material over a wide range of frequencies. So depending on the sample type, you can do different activities. So the first example is a cylindrical cavity, where if you have a small token-shaped material sample, you can put that into the cavity, and it looks at the S21 parameters of how the signal is propagating through the cavity, and it can calculate the relative permittivity and loss tangent of the material. We've also got split post dielectric resonators, where if you have a sample sheet, like a thin flat sheet of 1 mm thick or like 0.1, 0.5 mm thick, you can slide it inside the cavity. And again, looking at the Q factor, you can actually calculate the relative permittivity and loss tangent of the material. In case of conductors, we use a single dielectric resonator, in which case you can actually pass on a metallic sheet within it, and it will tell you the conductivity and sheet resistance of the material. Then we also have the waveguide technique, where you can see between the 2 waveguides, you can slide in any material you want, and as the signal passes through it, you can calculate the permittivity and loss tangent through a MATLAB script that we have created. Over here, I've specified 8.2 to 12.4 gigahertz, but we can actually do anywhere between, I think, 0.5 gigahertz up to 70 gigahertz. We can measure at any frequency band we want. And then there's this Damascus open cavity resonator kit, where you can again put a thin sheet sample of the material in between, and it measures the relative permittivity and loss tangent over a wide frequency range of 10 to 65 gigahertz. So we can use these sort of different techniques to actually characterize any material we want. So here's an example of what 3D printing can do. This was a very simple project that one of our master's students, our undergraduate student did, where he designed this massive 16 by 16 antenna array, which gives you a highly directional beam, but it's not circularly polarized. By developing this 3D printed structure on top, which is just a very, very simple 3D printed structure, you can actually generate an axial ratio below 3 and hence achieve circularly polarized beam. And as you can see over here, your axial ratio simulated versus measured is under 3, which basically means this can generate a circularly polarized beam and has a very strong gain from 29 to 31 gigahertz, all providing a gain over 16 dB, and hence confirming that this sort of antenna does work over a wide range to achieve the required axial ratio. So you can see how 3D printing can actually make a difference in terms of just generating from linearly polarized beam to a circularly polarized beam. Now, if we start adding these air gaps in between, as I said, it will start allowing you to change the relative permittivity of a material. Here's an example of PLA, which is a very common thermoplastic, which is used in 3D printing. At 100% infill density, you generally get a relative permittivity of 2.7. But if you reduce the infill density to 80%, you would get about 2.4. When I say 80% infill density, it basically means there is 80% material in it and 20% air gaps. For example, over here, you can see this structure. This has about 10 or 15% infill density, which means only 15% of the area is material and rest is air gaps. And you can do simple crossing structures, cross paths, brick-like structures, these honeycomb structures. There are different architectures that you can use. They all have slightly different impact based on what frequency you're operating at, because you have to think about the size of the structure. If these periodic unit cells are very close to the lambda by 2 or lambda by 4, they would impact your frequency range accordingly. If theoretically practically there's no limit on frequency where you cannot use 3D printing, but obviously as you go higher in frequency band, your response degrades if the quality of 3D printing is not good enough. And that also is because as you go higher in frequency, your skin depth becomes more and more obvious and more controlling of the nature. So now, because you can change the sort of relative permittivity of the material, the question comes, can I do something interesting with it? So here's an example of what we did. We 3D printed these ice cube trays and we started filling them with silver ink in them. And with these metal inclusions into the structure, we could not just only change the permittivity of the material, but we could also change the permeability of the material, and we could actually introduce a magnetic material into nature that we can start using for different sort of applications. And as you can see over here, it changes our permeability from 0.7 to 1. And it is an anisotropic material. And by anisotropy, I mean your relative permittivity and permeability is different when you're looking through x-axis versus when you're looking through y-axis versus when you're looking through z-axis. And hence, with the change in permittivity and permeability in different directions, you can introduce very new control on electromagnetic waves that can do completely new applications. Here's the structure that I just talked about, where we actually 3D printed simple structures and then just put some silver ink in it. And as you can see, how the permittivity and permeability of the material changes when you're measuring like this versus like this. So you can see how your permittivity and permeability is changing in both dimensions. So here's a simple antenna structure that one of our students 3D printed. So the substrate was 3D printed and a simple copper tape was used on top. And because of how the structure was designed, how the material structuring was designed, it will again achieve like a very good circularly polarized behavior at about 3 gigahertz, as you can see over here. So again, because you can change the relative permittivity of the material with variation in density, you can achieve lensing behavior. Any sort of convex lens that we know of, how it works is there is the path of travel for a light in middle is much larger than the path of travel on the top or at the bottom. And hence your spherical wavefronts, as they pass through your lens, they take much longer to travel in the middle versus they're much more quicker when they're going from top or bottom. And hence by the time the wave comes out, your optical wave becomes a planar wavefront, which gives you a highly directional beam. It's the same behavior over here. Instead of having that convex shape, we change the permittivity of the material. When there's higher permittivity of the material, your speed of light reduces, and hence your electromagnetic wave will travel slowly wherever the permittivity is higher. Wherever the permittivity is lower, that's where the speed of light will increase, and hence that signal will travel much more quicker. So as you can see over here, epsilon 1 is the highest permittivity, and hence the signal travel the slowest over here versus on top or bottom, and hence this spherical wavefronts can be converted into planar wavefronts. Here's a CST simulation showing the same thing, where your circular wavefronts, as they pass through the lens, they travel the slowest in the middle and much faster on corners, and hence you start achieving these planar wavefronts, which shows how your beam suddenly became highly directional. This is a 3D printed version of the lens that I just talked about. It has very high permittivity in the middle, and that is because we used very high infill density. It's 100% over here, so it's about 2.7, then 80%, so 2.4. then 60% infill density, so permittivity of 2.2, then 1.8, 1.5, 1.2, and then air. So this actually behaves as a proper convex lens and redirect the beam wherever you want, and make the beam highly directional. So these sort of 3D printed structures, they're very easy to manufacture. As you can see over here, we can actually make them in a basic 3D printer. As you can see over here, it's basically just doing that 3D printing, and you can see how much air gap it is introducing on the corners versus in the middle, there are literally no air gaps. So here's an experimentation validation of the structure. So this is our anechoic chamber with massive positioner that can rotate. It can hold very heavy antennas in there. And as you can see, when you put a lens in front of it, the antenna gain increases by about 10 to 14 dB. In reality, the antenna that was being tested has a gain of about 6 or 7 dB. But because of the introduction of the lens, we could go up to 18 to 22 dB. So depending on how the lens is designed, you can actually get a gain improvement of anywhere between 7 to 14 dB. And these sort of lenses can be printed within a couple of hours using 3D printing. They're very easy to develop. And there's now a lot of work showing how these lenses work. There's another very interesting thing we did using the anisotropic behavior of the material. So here, as you can see, red is a material with permittivity 6.5. and white is the material with permittivity 3. And we try to do a bifocal lens behavior. What does it mean? As a signal enters, it behaves as a bifocal functionality, where if the signal is at 9 gigahertz, it automatically turns left and you get the material and you get the signal coming out at 9 gigahertz on the left. If it is at 10 gigahertz, your signal will always pop out on the right, and hence the bifocal behavior. Again, this was fully 3D printed. A computational optimization algorithm was used with inverse design technique to actually generate this 3D printed structure, the actual design of the 3D printed structure. This was first validated in CST, and then we actually fabricated it. The fabricated version is all white, so you can't really see the difference between the two materials, and hence we use this red and white distribution as a graphical image to actually show how different they are. And as you can see over here at 9 gigahertz, as the signal enters from here, it exits from top. When it is at 10 gigahertz, it exits from bottom, and there's nothing going on top. And hence you can see the bifocal nature. Again, completely 3D printed structure. So there's a lot of work that's going on in reflect array structures and and metasurfaces. You can also develop metasurfaces and reflect arrays or frequency selective surfaces using 3D printing. Here's a very simple example of how 3D printing is being used to create a reflect array structure. It has a copper back behind the structure, and based on the size of each unit cell, as you can see over here, this structure, this unit cell is much bigger compared to any other unit cell. So this offers a different phase delay compared to any other element, and that's the phase delay distribution that we are trying to achieve. And now, if any beam that hits the surface at a fixed angle of 0 degrees, it always gets reflected at 45 degrees, and it becomes highly directional. And as you can see, your measured gain is about 27-28 dBi, and hence it can actually be used for different space applications or different ground station antennas. Instead of having massive dishes that we have at our homes, this can actually be reduced to about 10 by 10 centimeters, this small. And this is how 3D printing can also allow you to achieve very highly directional beams. Here's another example of, again, 3D printing being used to convert a linearly polarized beam into a dual circularly polarized beam. So it generates both left hand as well as right hand circular polarization. So you can see over here, the red elements are vertical in line, while the blue ones are horizontal, and hence they're reprogramming the beam, the incoming beam in both right and left circular polarization. And hence you get a dual circularly polarized beam where your axial ratio is under 3 for both of them. They both have similar gain performance as well as similar aperture efficiency. And all of this is possible because 3D printing allows you to generate any sort of these 3D structures, which is practically not possible in a regular use case. Again, we can also do metallic 3D printing. So metals are also another way of another very interesting factor where you can extrude aluminum or silver and actually keep on layering it up to create interesting 3D structures. These are called FFF techniques or FDM techniques, fused deposition modeling. And here we are using this metallic 3D printer to create this simple transmission line on a 3D printed substrate. So the substrate as well as the transmission line on top, both were 3D printed. And as you can see, the S21 performance of the transmission line is very similar to the one printed on a simple Rogers structure with copper. Versus the silver ink, they both have very, very similar performance as we go over a wide range of frequency. So this sort of 3D printing technique also works. So we started creating frequency selective surfaces. We started creating filters out of it. And what was the most interesting part about these filters? As we increase the thickness of layer of these conductive loops, these split ring resonators, we could see the change in the bandwidth of the filter. And as you can see over here, with the change in height, when it was 1 mm, your 0.035 mm, your band was much smaller, versus when you make the thickness higher, your bandwidth improves. We've conventionally we've always seen this bandwidth improve with the change in height of the material of the substrate. But this is also now true, that we can validate that it is also true when you increase the height of your copper or your conductor layer. And that's what we are presenting over here, that with the change in the thickness of the conductor layer, you can again change the bandwidth of your filter. And here's an example of a thinner structure versus here's another example of a thicker structure that we validated at a higher frequency. Okay, so yeah, going ahead, this is an interesting structure we tried to create with 3D printing again, and combining both 3D printing and metal molding. So there's a metal called Fields metal, which has a very interesting melting point of 62 degrees centigrade. But 3D printed structures melt at about 200 degrees centigrade. What we did was we 3D printed this interesting structure with a loop inside, and then we put it into a hot water bath of 75 degrees, as you can see over here. And then we inject this alloy in there, the Fields metal in there. So whenever, and then when it cools down, it's a solid structure. When you heat it up slightly, it flows out, and you can actually control how the flow works. So you can actually create a very interesting, this 2D table, where the interesting part about it is there's a simple horn antenna on top, and whenever you place an object anywhere, it will detect if there's an object placed on top of the table. So you can actually create these sort of very simple split ring resonators or like coil resonators using these 3D printed structures in a 3D shape rather than 2D structuring, and create these sort of sensing equipments very easily. We also tried to create simple capacitors. So again, this is just a simple capacitor by 3D printing a ceramic and then filling it up with a conductor. And that basically provides you an excellent quality shunt capacitor. We also did a lot of work on conformal metasurfaces and conformal 3D printing. So we can actually 3D print any sort of conformal shape, as you can see over here. And then we can use an inkjet printing technique to print silver using silver ink. We can print on top of the conformal shape. So you don't have to have a flat surface to 3D to print your electronics on. We can actually do that on curved surfaces as well. And how we did it is by modifying a 3D printer. So we replaced the inkjet head, like a regular inkjet head that just goes straight. We added a new inkjet head that we created, which can actually tilt in different directions as well. And because of that tilting, whenever there was a curved surface, we could actually tilt the head, print it on that. And as it is going straight, it will keep on bending accordingly. And this sort of 3D printing and inkjet capability allows you to print on any sort of conformal structure or any sort of conformal shape. So these were some of the work that I showed about 3D printing. Now we'll go to the second interesting topic that we did about novel beam steering antennas. What sort of different beam steering antennas that we've been working on? What are some of the current results? So a lot of our work was focused on leaky wave antenna structures and how leaky waves can be used for different sort of beam scanning and beam steering capabilities. Over here, we are showing a simple bow tie structure based leaky wave antenna, where because of the variation in spacing between each element on the 4 antennas, you can actually change the beam direction. And using SPDT switches at the back, I can select which antenna am I feeding to. And hence over here, as you can see, I could get a gain of over 12.5 dB throughout the frequency band of 27 to 30 gigahertz and steer the beam for about 65 degrees and hence achieve a proper one-dimensional beam steering. However, because it's a leaky wave antenna, with change in frequency, there's a shift in phase, which basically changes the beam direction with the change in frequency. That's called beam scanning leaky property of the leaky wave antennas. And I wanted to get rid of it and create a new sort of antenna. So I started looking into substrate integrated waveguides and how these sort of antennas work. So substrate integrated waveguides are an excellent technology. We all know what SIWs are. They have two copper planes on top and bottom, and they're connected with each other through wires. Now the big issue is a regular SIW tends to have thousands and thousands of wires, which basically makes them extremely rigid. It is difficult to bend them. Makes it very difficult to fabricate. It becomes very costly to manufacture, and there is no DC biasing capability. I cannot put a pin diode on it anywhere because everything is connected. There's no separated ground plane versus a top plane. So I started developing how I can improve this functionality, and we came up with this corrugated structure where I can replace these wires with corrugations, which makes it function for a particular frequency band. It only operates in TE10 mode, but it does work as a proper waveguide. However, this is a bit more lossy. So this one, a regular SIW generally offers you a loss of about 0.4, 0.5 dB per 10 centimeter length at 30 gigahertz. While this one offers about 2 dB loss per 10 centimeter length, which is a lot. So we started playing again with how these corrugations work and how can we modify the structure. And we come up with this integrated digitated capacitor structure where we have this IDC finger-based structure, intertwined finger structure, and that introduces new capacitance into the system and reduces our losses quite a lot. And now we have an average loss of about 0.6, 0.7 dB per 10 centimeter length, which is very close to an SIW. And because there are no wires involved, no the top plane and the bottom plane are separate, I can start putting pin diodes in it. And as you can see, the S parameter response of it, the S21 validates it quite well of how good it functions for the TE10 mode. When I say TE10 mode, that means it starts working at about 20 gigahertz and it operates up to 40 gigahertz, and then it starts losing its energy. It is supposed to work further ahead, but the quality gets worsened. So it has the equivalent circuit of how the LC components of the circuit works and how it operates, and we have validated it both in simulation as well as through analytical results. So one interesting parameter that we came up with this IDC structure is, as a regular SIW, as you can see, when the signal enters, it just goes straight, as you can see over here. But if I start filling these gaps with pin diodes, and if I activate pin diodes in a certain region, so for example, I've activated these 5 pin diodes over here, this would suddenly change my beam propagation. So as my EM wave is passing through it, when the pin diodes are forward biased or they're powered on, it suddenly goes into these corrugations. These U-shaped slots will start radiating. If there's a regular slot over here, it will stop radiating. And then once it is back to the normal function, the signal will come down and will travel again normally. So now, in a regular case, my regular slot will radiate from the bottom, as you can see over here. But in this case, my U-shaped slot is radiating from top and going sending the beam downwards. So now I can switch the beam between 2 different directions. Now, what if I add these unit cells multiple times and then do a combination of these radiations? I can actually have a continuous steering between the 2 points. And this is what we achieved by creating this 6-element SIW antenna with the 30 pin diodes on top. There are 6 control lines. Each control line chooses if this particular slot is radiating or the U-shaped slots are radiating on top. And then based on that, I can actually get an excellent performance throughout the 26 to 29 gigahertz bandwidth. As you can see over here, these are the radiation patterns showing that the antenna has a gain of about 13 dB throughout the frequency band. And there's a massive overlap between each band because it's a leaky wave structure. So it provides you a fan beam, which is very directional in elevation angle, but highly a very wide beam width in the azimuth angle. But it shows that my overall beam works from plus 60 to 0 degrees in plus 20 degree elevation, and minus 10 degrees elevation for the second feed from minus 60 to 0 degrees. Now I wanted to update this antenna because there's a break over here and I want a full beam steering from plus 60 to minus 60 degrees. So what can I do to actually achieve that? What I did is put 2 of these antennas together. next to each other, as you can see over here. And basically, because of this overlap, I could actually achieve a full 120-degree beam steer, starting from plus 60 to minus 60 degrees, with a good enough overlap to actually keep on switching between the antennas. And I also have a second beam steering and elevation axis, where I can switch between plus 15 degrees and minus 15 degrees and change my beam direction anywhere I want, while maintaining a gain of over 12.5 dB. And again, this operates in the whole frequency band of 27 to 30 gigahertz. Now, one interesting thing was, if I want, I was developing this sort of antenna for a 5G base station operating at millimeter wave bands. And for a base station antenna, it needs to have a gain of at least 20 dB. This is, however, limited to 12.5 dB. So I thought lenses, I've developed quite a lot of lenses before. Can I not just put a lens in front of it and increase its gain by about 7-8 dB? And that should do the job. However, when I started using a regular lens that I had showed you earlier, with any sort of traveling wave antenna or a leaky wave antenna, I saw that the performance degrades drastically. So for a regular standing wave antenna, like a patch antenna or a horn antenna, my one-dimensional lens has a gain improvement of 7 dB. My two-dimensional lens will have a gain improvement of about 14 dB. When I put the exact same lens in front of my traveling wave antenna, my gain improvement decreased to 3.9 dB. And in some cases, it actually went down to 2.5 dB. So this was a question of worry, like, why is this same lens, when it is independent of antenna, independent of size, is not working for my new antenna? And when I started looking into it, I realized there are two key reasons behind it. First is because it's a leaky wave structure. All my unit cells, so each radiating element has a phase delay in it, because how leaky waves work, when the signal enters, when it reaches the first element, it radiates out some power, it reflects back some power, and then the rest goes to the second slot. So every other slot or every other radiating element has a phase delay in it, number one. Number two, there's a reduction in amplitude as well. So I started using this reduction in amplitude and phase change to actually monitor how my phase center of the antenna changes over a long surface. And instead of having a phase center, I started coming up with a phase surface. Where does the phase surface or the phase line for a one-dimensional leaky wave antenna lies? And that's what started helping me to develop a new sort of lens. So as you can see over here, a planar lens, when I just incorporated phase, I could just tilt it at a particular angle and that should work. That just improved the functionality a little bit by about 3 dB, not to the same level. And then I started adding the amplitude correction. And with the amplitude and phase correction combined, I got these very interesting logarithmic shaped lenses, which started giving me about 7.58 dB gain improvement, which is in line with a regular lens. Interestingly, if I feed the properties of a standing wave antenna, like a horn antenna or a patch antenna, into my math, into the equations for this, it will actually give me this flat lens again, which basically shows that these equations or this math is valid for any sort of lens design that we need. And now that we have much better performance, I can put this lens with my antenna, and I created this very interesting 3D structure with 6 antennas in there and 6 of these lenses. The overall structure is 90 by 90 by 90 mm, so only 9 centimeter cube worth of area. And it has this is how the two sides look like, and you can just put them next to on top of each other, and it provides me a gain of over 20.5 dB throughout the frequency band, while offering a full 360-degree beam steering as well as an elevation beam steering, which now I can use for any sort of 5G base station applications. One of the companies in the UK is now currently using this antenna to test their other base station antennas, as keeping this as a standard in their anechoic chambers, and then testing all the other antennas, comparing their performance with this antenna. So, and hence this is now being practically used in real life applications. These lens-based applications, we have also used, we've also created quite a lot of radar sensors that are now being sold in the market, and the lens at the end of it were designed by us. There's another very interesting lens-based beam steering antenna we had created for a satellite applications catapult, and it's called a Lundberg lens. So a Lundberg lens has very high permittivity in the center, and as you come out, each shell keeps on reducing its permittivity. It's a massive 3D printed structure, and you can put a phased array at the bottom. So phased arrays, they tend to have issues like At the edge angles, your beam is low gain. The gain drops drastically. Your aperture efficiency reduces. The power consumption is very high. So we are trying to address all these issues by introducing this new Lundberg lens loaded phased array system, because this Lundberg lens allows you to reconfigure the beam direction much more easily. Phased arrays, they work when all the elements are active simultaneously, and hence it consumes a lot more power. Using Lundberg lenses, you can only activate one element and steer the beam around. So how does it work? Based on the location of the element, if I activate the element on the very corner, it basically redirects my beam towards right, and hence I can steer my beam anywhere between plus 55 degrees to minus 55 degrees, and this can be changed based on the size of the lens. And hence, if I bring my antenna in the center, it radiates straight up. If I bring it towards the left, it radiates towards the right, and hence I can keep on changing my beam direction. And because it's symmetrical to the middle, the same thing applies if I do it in azimuthal axis versus elevation axis or anywhere in between. I can have a full 2D beam steering wherever I want. So we started creating a full architecture of how this antenna would work. We had different beamforming ICs. We recreated a whole phased array architecture, and we started putting it together. And this is what the final antenna looks like, where we have the lens as well as all the control unit inside the structure. And as you can see over here, it has an excellent beam scanning capability of plus 55 to minus 55 degrees while maintaining a decent gain of 17 to 18 dB, making it highly relevant for any ground station applications. What we are majorly using it for position, navigation, and timing. How can we achieve PNT services from low Earth orbit satellites, which has not been achieved yet by anyone globally? So what we did was we put it inside the anechoic chamber. The antenna elements was connected to a beamformer, as you can see over here, and then we were rotating the probe, as you can see over here, at a fixed speed. So when we rotated the probe at a fixed speed of about 4 degrees per second, our algorithm would actually switch the beam every time my beam power reduces by about 3 dB from the maxima. As you can see over here, my first beam continuously keeps on going. When it reaches its maxima, it records that value. My beam is still connected there. But when it drops down by 3 dB, it suddenly switches to second beam, and hence it always maintains this pattern, which shows that your antenna, even if it is moving at a very high speed, maybe on a car or an airplane or on a train, it will never lose connection from any satellite. It will keep on switching its beam based on how the direction of the satellite or how the direction of the antenna is changing. So again, reconfigurable intelligence surfaces was another key area that we started looking into, which is again for which is again for beam steering on how we can steer the beam around. It's commonly known that you can use pin diodes throughout the metasurface, and with the change of beam the pin diode configuration, you can point the beam in a different direction. And that's exactly what we are trying to do over here. We have a simple antenna array, simple unit cell array, forming it into a reconfigurable intelligence surface. Each element is loaded with a pin diode, and with the reconfiguration of the structure, as an example over here, your beam direction is changed to 45 degrees. As the signal hits the surface, the reflected beam goes at 45 degrees. It works excellently, but we started questioning what happens when certain elements, certain pin diodes start dying over time on the structure, and we started studying how the performance gets affected. So what we did was we started seeing what will happen if some elements started randomly dying. So what if 5% of the pin diodes died on the surface, or 10%, or 15%, or 20%, or 25%? And we realized when we were looking at about 25% damage, my beam power dropped by about 4 dB, and my side lobe levels increased so much that the difference between the main beam and side beam is only 1 dB. And that's what became the massive problem. There are massive network security issues because of this now, because instead of pointing the beam where you're supposed to, you're pointing a second beam in a different direction, which a hacker or a spoofer can use to hack into your network or start affecting your network quality quite a lot. And then your network quality degrades over time. And this sort of damage can happen within a year of implementation. So it starts bringing up the question, is it actually beneficial? Is it actually important for reconfigurable intelligence surfaces to be used for future 5G or 6G networks? And we are now working on developing how we can improve the functionality, how we can improve these sort of reconfigurable intelligence surfaces, by using machine learning and make them self-correct themselves, and which is our new project which is ongoing right now. We did the same study. What if instead of randomized damage, if the damage was concentrated in certain regions, which will basically it shows how we're getting the same damage or same degradation in performance, but also there's a significant change in beam angle because of this. So our new project, which is anisotropic microwave terahertz metamaterials for satellite applications, is a new project where we are focusing on how we can create new anisotropic structures, and they can do excellent different activities. For example, one of the lenses we recently developed is it not just shows lensing behavior, so convert your widespread beam into a highly directional beam, but also convert it into from linearly circularly polarized beam, linearly polarized beam to a circularly polarized beam. And how it works is, as you can see over here, there's like this massive structure where each element, each portion of this element is provided a different permittivity in x-axis, y-axis, and z-axis. And how are we controlling it? We're controlling it with this simple unit cell, this cross-shaped unit cell. By changing the wx and wy parameters, you can see how the permittivity in x-axis and permittivity in y-axis are changing. And now I can select certain elements from this to actually create a full 3D structure of the lens. And as you can see over here, it shows the different cross sections of the lens. At different cross sections, you have different structuring, and this allows us to create a completely 3D printable structure that can achieve both a lensing behavior as well as convert a linearly polarized beam to a circularly polarized beam. And as you can see over here, our directivity is roughly 21 to 24 dB, while for the antenna, my directivity was only 12 dB. So I'm increasing my directivity by about 10 dB. And the axial ratio improvement, which went below 3 dB throughout the frequency band, and it matches really well with simulations. We've actually measured this lens, and it works really well. And one of the interesting factors that we studied is during 3D printing, how much was the effect in dimensions and how that change in dimensional properties was affecting the performance of the lens. And it shows that very small change of about 28 micrometers shifted our frequency band by about 1 to 2 gigahertz. So it becomes really, really important to understand during 3D printing process how accurate your dimensions are. So here's the final printed 3D printed lens. It's about 11 centimeter in diameter, 7 centimeters in thickness. And here are some of the results for it. So the lens with the antenna gives you a gain of about 20 dB and a directivity of about 21.5 dB. Axial ratio maintained under 3 dB for the whole frequency band. And there's a very good gain improvement of about 11 dB throughout, which is very similar to performance of any regular lens, while offering linearly polarized conversion to linearly polarized to CP conversion. And we can redesign these lenses for any frequency band we want. We can develop them for right-hand circularly polarized or left-hand circularly polarized beams. So going ahead, we created different sort of RCS reduction metasurfaces as well. So RCS is radar cross section, and the whole key point is how do we reduce the radar cross section, which is basically if, for example, an object is passing by and your radar needs to detect it, what happens is it throws a signal and it looks at reflections. Now, if it's a pure metallic object like a plane passing by, you can look at the strong reflections coming back and you can recognize there's something passing through. But if the material on the plane is made from something else, for example, a metasurface or metamaterial, we can actually spread that energy everywhere so that the radar never receives the exact same signal. And this is what we're trying to achieve over here by simple dumbbell-shaped unit cell. And by changing how these unit cell is distributed across the surface, we can actually distribute the energy everywhere. So, for example, this is the original signal, and this is the signal when it was reflected from a simple metallic structure. However, when we put our metasurface over there instead, at 60, 70, 80, 90, 100, 110, 120 gigahertz, you can see my main beam has just appeared and the energy is being distributed everywhere, which basically shows the radar, which is actually which sent the signal and now looking at the reflections, it won't absorb it won't observe any reflections being received, and hence you can cloak any object from any radar. So here's the fabricated metasurface, and this was tested in our anechoic chamber. And you can see when we were using a simple copper plate, the radar cross section was about 10 dB, 10 to 12 dB. However, when we did this sort of metasurface, this radar cross section reduced to about -5, -6 dB on an average. And hence you can actually improvise the functionality quite a lot. This was at a lower frequency band of 20, I think 18 to 24 gigahertz. We also worked quite a lot on time modulated metasurfaces. So time modulated metasurfaces is how both integrated communication and sensing can take place. So how it works is, for example, if you're communicating at 5 gigahertz, 5.5 gigahertz, which was the case over here, at 5.5 gigahertz, you point a beam straight ahead, but you look at its harmonics at 5.500, 5.533, 5.51, 5.52, and you start using that to sense in different areas. And as an example over here, at 5.5 gigahertz, as you can see, my main beam is going straight ahead. At 5.5003333 gigahertz, my beam is splitting into two, which is the difference beam, and it is looking at two different angles. And this was simply controlled using a Raspberry Pi at the back with all the elements. Each unit cell has two pin diodes, and they were independently being controlled throughout the structure. And as you can see, there's a receiver antenna which can rotate 180 degrees, and there's a transmitter antenna looking at the power which is basically transmitting a power, and then this intelligent surface is reflecting it back. So this is our latest project that we are working on right now. It's called Transmeta, where we're looking at how we can make these sort of metasurfaces and antennas completely optically transparent, so you can see through them. So you can put them on windows, on vehicles, on trains, without actually requiring to put a very heavy equipment. You can have these planar structures hiding in complete plain sight. You can use them for AR, VR glasses. You've seen the new Meta glasses that have come out, the new AR glasses by Apple, how we can hide quite a lot of electronics just in plain sight on the glass, so you don't have to have a very heavy equipment to carry around. And we're developing that technique for RF systems. So as of now, in the progress of the project, I'll show you some of the antennas that we've developed and how it works. And now we are in the process of developing some metasurfaces on this. So to develop any sort of transparent, any sort of antenna, not just transparent, we need two things. We need a substrate and we need a conductor. Substrate is pretty common. You can use glass, you can use acrylic sheet. There are multiple optically transparent options available in the market. The conductor is where the big problem comes into picture. So what we did is we started using three different types of materials. The first was indium tin oxide, which is a very known very commonly known formulation, which is optically transparent but low conductivity. Then we started creating these mesh structures, which is like mesh made of silver ink. So these mesh are of size 0.5 microns, and hence they are completely optically transparent to human eyes. You can completely see through them, and they provide you much better conductivity. And then there was another version of the same mesh. We had created different sizes, different structures, and we've been using these sort of structures to create different sort of antennas. And as you can see, this is the optical transparency of the antenna, of these sort of transparent films that we had created. So 91.5% compared to completely plain sheet. The light transfer is about 91.5%. So you can see how extremely transparent these objects are. And we did like a massive study about understanding how the mean sheet resistance changes for different points for different sort of materials, for different sort of pitch density, and how these nanowebs are designed. And we're using these. How are we measuring it? We're using two waveguides, and we're putting the sample sheet in between, and we're looking at the S11 and S21 performance, and using the math provided here, we can actually calculate the sheet resistance of the material at any frequency band at different waveguides, as you can see over here. And here's like an experimental setup where you can see here's the optically transparent nanoweb sample that we had placed between two horn antennas, and we are putting them together to actually do the measurements. And here you can see the real conductivity versus frequency, how the conductivity of the material changes over frequency, and hence it will help you make a better decision of what material to use for any particular frequency band of operation that you're designing it for. And we did the same thing for using different techniques. We used 4-point probe method, where you put 4 probes and then measure sheet resistance and flow of current from between different probes, and use that to calculate the conductivity of the sheet. We also use single post dielectric resonator. We also used waveguide techniques, and then we measured optical transparency, but just passing light through it. And then we started creating these sort of antennas. So you can see these are optically transparent antennas. I actually created them by my own hands in the lab, and hence you can see my thumbprints on them. One of the big problems was I cannot actually solder a connector directly on the antenna. So I have to find a way to actually send the signal onto the antenna. And hence I started developing these coupling technique through which we can transfer a signal from a PCB to an optically transparent structure. So how does this work? There are two different methods I looked at. The first was a simple CPW to CPW transition, where you have first CPW, second CPW, you just put them together. The conductors are in contact with each other and hence signal transmits. And the other is a coupling based technique where I create this tiny ring coupler, a circular coupler, which couples with the CPW line to the microstrip line. And this is how the data is being transferred. Now we'll see what are the pros and cons of both of them. The first method works fabulously. It's an excellent technique. You can see the signal transfer is excellent within 3D. There's less than 3 dB insertion loss from 0 gigahertz to about 45, 50, about roughly 50 gigahertz. Big problem is the gap between the CPW line versus the ground plane is only 0.2 millimeters. So it becomes really difficult to align them together. Even if 0.1 millimeter of shift, you suddenly start losing performance, and 0.2 millimeter of shift, your CPW line is touching the ground plane and you completely lose the signal. And hence it is very, very difficult in practical scenarios to maintain it. So we started coming up with the second method of coupling, where using this coupling technique, there's no ground plane coming in contact with the other with the microstrip line, and it completely gets rid of the problem and still provides us the same performance of 0 to 48, 49 degrees. Oh, sorry. So 0 to 48, 49 gigahertz. However, our losses have increased a bit. Now it performs at about 3 dB loss. But you can see there are certain points where the loss is very minimal, and you can reshape these couplers for any application that you're developing. And you can reshape, you can reshape these couplers for any frequency you're developing. So these couplers will increase or decrease in size, and that will move this central point to left or right, and hence you can improve your beam transparency. And now I've got a method to actually transfer a signal from my PCB based layout to an optically transparent antenna. So how was this antenna created? So I took a simple substrate, which in this case is a PET substrate, roughly 1 mm thick. And then I use this optically conductive, optically transparent adhesive. I stick that adhesive on one side and then rip it off, and then put the PET substrate that has the nanoweb on top, and then put a protective layer on top of it, and then do the same thing on the other side. And that's why you see it has 11 layers stacked to create one simple patch antenna that you can see over here. And then we basically couple them with any sort of structures. So once we had worked out the technique, we actually got a company to build one, which you can see over here is much more cleaner compared to the one that we made in the lab. However, they both work exactly the same. The performance is exactly the same. And now we wanted to test if this sort of coupling technique actually works. So what we did is we tested it with a simple patch antenna. We put the coupling technique in force. And when we put the clips next to them, you can see there's a slight change in S parameter performance. However, the antenna still works. My beam performance is still there. Now, when I look at the radiation patterns, again, I'm getting the right radiation patterns. My beam is in the right direction. So I can confirm that the signal works. What is the most interesting and important thing to notice is how the efficiency changes. So when you create a simple patch antenna with the regular substrate with the copper line, you get a patch efficiency of a patch of about 65-70%. But when you go to optically transparent structures, your both conductivity is reducing, your dielectric losses are increasing, and hence your efficiency drops down to about 37-38%, as you can see over here. This is the simulated performance without any transition. I'm saying this is when I'm assuming that my connector is right here. Now, when I re-simulate it with the transition, so I move the connector down here, there is slight loss of about 2%, 3% in efficiency, but not a significant loss. When I measured this antenna with the connector, I can actually see my measured total efficiency is actually very close to my simulated results, which confirms that my this transition actually functions really well. So this was validated at 10 gigahertz by using a 10 gigahertz patch antenna. And then we created more. We created another patch antenna at 27 gigahertz, and we ran this exact same experiment to see if this would actually function. To our surprise, again, the total efficiency was very close to our simulated results and to the simulated results without transition, which confirms that this overall antenna system with these sort of translations actually work really well. And we can use them for any sort of applications in the future. And now we've been using these, as you can see, for more different sort of antennas. And we have started coming into a position where we are. I actually sent one metasurface completely optically transparent to manufacture today, and soon we will be measuring how these metasurfaces function and how these metasurfaces work. Optically, completely optically transparent metasurfaces would work. So yeah, this was a list of some of the work that we've done at Loughborough. This is mostly my work and my colleagues at Loughborough. I would like to thank Professor Will Vito and Tom Whittaker, Shiu Zhang, who've done quite a lot of work with us. Amit Kumar Patel, one of our postdocs, new people joining us. All of this are their efforts combined together in the research group. If you guys have any questions, I'm happy to answer. In our group, we do keep on looking for new PhD students. We do keep looking for research fellows. If anyone is interested and have great ideas they want to work on, please feel free to reach out. If you scan this QR code, it will give you my email ID. It will give you my contact details. You can reach out to me at any point. Thank you. I'm happy to take any questions you might have.
Any queries from the participants?
Hello.
Hi, Abhishek.
Sir, good evening.
Yeah.
Sir, actually, you shown in a slide that you have designed a microstrip antenna or some kind of antenna on a conformal surface using 3D printing.
Yeah. Yeah.
So, but sir, I want to know that how you have simulated that.
You can simulate a normal conformal patch antenna quite easily in CST.
So, how a planar surface is just taken on a conformal surface.
So CST does have a function to create these sort of conformal shapes. You can put a simple wave equation and convert it into these planar sheets. Or you can, once you've created your antenna design, which is planar, completely planar, there are functions in CST to actually fold them or conform them in particular shapes. If you Google conformal antenna design in CST, you will find a lot of videos demonstrating it. Or just go to the modeling section of CST, and there are functions to create either just simple bending or a waveform bending or like different sort of shapes. You can definitely very easily do that. Or if nothing, you can always code it in Python and then run that along with CST, and that does the job.
Okay, sir. Okay. Thank you, sir.
Any other questions?
Good evening, sir.
Hi, Pramod. Yep.
Yeah, sir. In general, so many cases, micro filters and other cases in antennas or beamforming cases, we are using pin diodes and diode cases. No? In general, diodes sometimes it will generate noise, sir.
Mm-hmm.
How we will generate the effective efficiency in the case of beamforming issues?
So diodes in general do generate noise, but that becomes a problem at very high frequencies. At lower frequencies, that is really not a problem. But if you do see these sort of issues, there are new techniques like FETs and MOSFETs, CMOS structures that people have started using, which basically offers much lower noise.
In general, we are using nowadays. We are using all our 5G and more than 5G millimeter wave frequencies only. No, sir. First, most of the application in IoT devices or any other applications also we are using higher frequencies only. But such cases, how it is effectively feasible for other real-time scenarios, dynamic cases?
Sorry, can you repeat the question?
In general, nowadays we are using higher frequencies only, na, sir. Millimeter wave frequencies or any other higher 5G or 6G application point of view. So nowadays we are designing antennas or any other relevance of applications, IoTs also. For
There are a
such
lot of pin
cases,
diodes
if we
now
do
available from
these type of
Macom.
antennas,
Yeah.
is it feasible or not with that principle, with that technique?
It is definitely feasible. There are a lot of work which uses CMOS and FET based diode structures that can offer you very very low noise. Irrespective of that, if you go to Macom or if you go to Infineon, there are few companies that have actually started manufacturing diodes for very high frequencies. So I've recently bought some diodes which function at 60 gigahertz, and the noise figure on them was, can't remember, but it was very very low. So the issue of noise introduced because of diodes or any sort of active elements is dropping down quite a lot. So I don't think in reality, when you actually develop these sort of antennas or filters or any sort of microwave device, noise figure of the diode would be a significant factor at these frequencies anymore.
Okay, sir. Thank you, sir. Any further research related to in this domain, sir? Can you suggest any topic related to, I mean, topic or I mean, in the case of any future research works related to this field?
There's a lot of work on these sort of beam steering antennas and new holographic antennas, holographic metasurfaces. I think that's one of the biggest fields right now. Besides that, you can use 3D printing and combine it with reconfigurable surfaces, reconfigurable antennas. There's also a lot of work on developing full RF system rather than just the antenna or just the diode or just the filter. People started developing full RF systems engineering approach to get the full performance of the antenna. So there are a few of these areas that are getting very popular now. If you go very high in frequency, quantum engineering is getting very popular, and there's a lot of work on RF and microwave applications of these sort of quantum-based techniques.
Yes, sir. How it is possible to implement the antennas with the quantum principles? That the logic gate principle is different, no? Quantum IBM quantum computers is there.
That's a different field. It's a new emerging field. Not everyone understands it right now. But most of the communications within the quantum-based equipments or quantum electronics is through waveguides because they happen at very very high frequencies. So there's a lot of work now going on in figuring out how we can create terahertz link between 2 points, which can provide almost zero latency data communication. So if you want, you can start looking at that.
Okay, sir. Shall we communicate in through mail for, because we are waiting for the postdoctoral positions in any foreign countries. So is
Yeah,
it
you can
possible
always
to?
drop us an email. I put my email on in the chat. So if you have
Yeah,
any
sir. Yes,
questions or
sir.
anything you want to know, you can always drop me a message.
Thank you, sir. Thank you so much, sir.
Any other queries from the participants?
Sir, good evening, sir.
Hi, Dhanan. Yeah.
Sir, can you give any guidance about the PDF in your university, sir?
You mean postdoctoral positions?
Yes, sir. Yes, sir.
So postdoctoral positions in the UK are driven from the fact when they have new project fundings. So, for example, we recently received a funding and we were looking for a postdoc, and the deadline for it was 1st of September. Now we are in the hiring process for it. So if you go to websites like jobs.ac.uk or just reach out to professors you can find their contacts from university websites. They'll be able to inform you if there's an available position. Most academics, they post their new postdoctoral positions on LinkedIn, or on almost every university website there is a jobs and vacancies page where all these are advertised. But again, it's very specific to field, very specific to subject. I'm hiring a postdoc right now, but I think we've already passed the deadline for it as well. So there are no then the applications were being accepted till like 10th of September, so till yesterday. So it depends on what you're looking for. You have to reach out to right people.
Okay, okay, sir. Thank you, sir.
But what I would recommend is if you're going for postdoctoral positions abroad or like anywhere, especially in UK, what we look at is what kind of publications you've got. You may have only 3 papers, but those 3 papers should be excellent in quality. They should be in top journals. I can tell you right now, I've shortlisted, I think, about 300 CVs so far. I've gone through about 300, 400 CVs so far. We've barely shortlisted 20 people out of 400 CVs. And our very first matrix to shortlist is what quality papers they have. We don't look at the number of papers, we look at the quality of papers and how relevant they are to the project. So if you don't have excellent papers published, it gets really difficult to go through the process.
Okay, okay, sir. Thank you, sir.
Any other queries?
I think this is it. So if there are no more questions, if you have
Yes,
anything you want to talk about, you can scan the QR code and it will give you all my details. You can drop me a message at any point you want. My LinkedIn is available there. You can email me at a.bansal@ilboro.ac.uk if you want to have just if you want to want to get answers to certain questions, or if you just want to discuss new ideas. We are happy to provide support with fabrication and measurements if you don't have that option. But if you're trying to do some interesting work, feel free to reach out and we can see the possibility of supporting you.
so at terahertz frequency, you have the measurement facilities there?
So in my group, we can do up to 70 gigahertz, but we have a sister group that can go up to 9 terahertz. It depends on what you're trying to develop, but we can do the measurement.
Okay. Thank you. So which means substrate supported at terahertz frequencies? Is it polyimide or some?
It's almost none of the regular ones. It's mostly silicon, gallium arsenide, those sort of wafers that work at that high frequency. The losses are very bad at very high terahertz bands.
So can we get that substrate in means India means
You probably can, yeah. Silicon wafer is available everywhere.
can we use it directly as we use the Roger substrate or
They generally require laser-based ablation techniques. You cannot put an SMA connector for 100 gigahertz signal. You need to have waveguide-based inputs because the connectors don't work beyond 65 gigahertz. I think the last connector that operates is at 65 or 70 gigahertz. Anything beyond that needs to be fed through waveguides.
okay? Thank you. Any other queries from the participants?
Sir, I have a one query.
Yep.
Hello, sir. Good
Yeah.
evening, sir.
Hi, Mohammed.
Yes.
Go on.
Yeah, sir. I have one query about that terahertz absorber, sir. In the range of visible light, if we want to harvest energy from the visible light, what are the aspects we have to take in mind for designing, and for what are the fabrication scenario can be done at the visible light range or the infrared range for the energy harvesting application for metamaterial absorber?
It's a very wide question that you've asked. I don't really have a specific answer for it. I think what you need to do is just read through quite a lot of papers about it, and that would show you what sort of parameters you need to look into. There are loads and loads of parameters that you have to work out. There are lots of materials that are available through which you can actually do different activities. But at the end of the day, it comes down to what sort of material you're choosing, what sort of fabrication requirements there are. So, for example, if you're designing, let's say, for 100 gigahertz or 110 gigahertz, which is 0.11 terahertz, which is still very low in terahertz, but very high in microwave frequencies, when you start fabricating, your minimum dimension would become about 20 microns, which you cannot do with simple lithography process. Photolithography won't work at that high resolution. So what sort of resolutions are practically achievable? You have to think about that
Yes, sir. That's
from
why I am
fabrication
asking about.
perspective.
Yes, sir. That's why I am asking about if we are designing for the 400 terahertz, like approximately nearby visible light, because the most
Why
of
do
the
you want to design
spectrum
something
is
for
belong to
400 terahertz?
sir, because the solar energy is in that reason, sir. That's why.
That's a completely different research field. It's not microwave or millimeter waves. This is not my
Yeah.
area. I know there are
Yeah.
energy engineers who does a lot of
Yeah.
work in that frequency range, in that sort of wavelength,
Okay.
where they're mostly working on solar panels and solar architecture. This is not something I
Yeah.
can advise on. Sorry.
Oops. Thank you.
Queries from the participants? I think there are no queries more, sir.
Okay, perfect.
On,
So if
on
anybody
the,
wants to reach out, feel free to drop me a message at any point. I'll be happy to have a chat.
yes, sir. On the behalf of the participants and MIT Group of Institutes, Ujjain, I extend my gratitude to Dr. Akash Bansal, sir, for deliver such a wonderful session, sir. Sir has explained in detail about 3D printed antenna, active beam steering, IDC based SIW, novel lenses for LWA, 3D grid lens technology, and meta surfaces. The clarity of your explanation of have enriched our understanding, sir. Thank you very much, sir, to contribute this FDP, sir. Thank
Thank
you,
you
sir.
so much. Thank you for the invite. All right. Thank you.
Thank you, sir. In the few minutes, our second speaker will join. Yeah.